Hi, welcome to the project demonstration of my signature project titled An Ensemble Model to Predict the Obesity Levels Based on Eating Habits and Physical Conditions. My name is Bhargava Udaygiri, and we are going to take a look at how machine learning models were used to classify the obesity levels in this dataset. Coming to the overview of the data that I have collected, it is an estimation of obesity levels, and mainly the individuals for this dataset were picked from Mexico, Peru, and Colombia. The dataset involves a total of 2,111 different individuals, and their ages vary from a low of 14 all the way up to 61 years of age, and they encompass a variety of eating habits among the population. And these people are also used to a variety of physical conditions that they undergo in their daily lives. And because of this and other factors, we have about 17 attributes where different features are collected from these people. And therefore, because of these number of attributes, the data set offers a comprehensive view of factors that could involve whether the people are obese or overweight. The main prediction variable in this dataset is a no obese DAD column, and there are 7 different levels for this predictor variable, ranging from insufficient weight all the way to obesity type 3. Features that I've used for the model training in this dataset are shown in this slide here. These contain 2 features less than the original dataset. These 2 features are whether the people smoke and the frequency of their smoking, and also whether the people are keeping a monitoring or a count of the calories they consume. These features were removed based on feature engineering and domain knowledge, which I'll talk about later. However, we can look at some of the data exploration that was done in order to better understand the data here. We can see that a simple data plot involving a histogram of the age population in the data shows a lot of positive skewness, where the data set is skewed right. This is because most of the age is centered around the 20s to 25. And looking at the height distribution, we do see a very normally distributed data set. However, it is also seen that there are certain groups with distinct ages, and they form peaks. So this could be like a multimodal pattern. And the weight distribution also seems to have a slight skewness, but not too much, and follows the same multimodal pattern as the height distribution, where there are distinct subgroups within the population where they belong to certain weight limits. Coming to the way the genders are distributed, we see an almost equal gender distribution. 51% of the population statistics collected were male and 49% were female. A box plot of the continuous variables like the age, height, and weight can be seen here. There are many number of outliers in the age box plot, and very few are non-existent when it comes to height and weight box plot. We can see the median weight right around here, and the median height at about 1.7 meters. Later, outliers were detected based on that, and this is a visualization of the correlation matrix for these numerical variables. We tend to see that height and weight have a very high positive correlation, which makes sense as taller people tend to be heavier. The weight and age also have a positive correlation, not as strong, which means that older people tend to be heavier. And based on the skewness, we saw this age distribution had a very high skewness of over 1 and nearly 1.53, and therefore this had to be transformed, which we'll come to next here. Data shaping. First, we will start with missing values. The dataset originally did not contain any missing values, so as per instruction, they were introduced into the dataset randomly for a few features. And while talking about what features I chose, I mentioned about how feature importance was checked. This was done where random forest on the dataset was employed, and then we checked for what features are important here based on Gini impurity values shown here. Based on these values, we immediately see that the smoke habits of the people and the calorie consumption monitoring has very less impact or importance in the dataset. And also, more importantly, based on the domain knowledge and the research that published this dataset, I decided to remove these features for my model training. Can also see that one of the other columns where frequent consumption of high calorific food also show a very less Gini impurity value. However, based on domain knowledge and how frequent consumption of high calorific foods do have an impact on obesity level, I decided not to remove, solely focusing on the Gini impurity value. Then, and naturally, these less relevant columns were removed from the dataset. And feature engineering, this is where a new column was introduced in the dataset, and this is the body mass index column where height and weight are taken and a number is associated based on that for obesity classification. And this later we can see it did prove to be a very important predictor in determining the overweight levels. And the algorithms I've used in this dataset include naive Bayes, because this is a classification task, and naive Bayes as a classifier is a very fast and efficient, computationally efficient algorithm, and also handles high dimensionality data very well. Support vector machines are used for regression and classification. However, especially for classification, I decided to go with this since it handles non-linear relationship between columns in the data very well, and also because they could act as like out of the box machine learning algorithm, especially when used for classifying tasks. And then decision trees were used, since decision trees tend to be very robust with generalization of data, wherein unseen data handling is very well on decision tree algorithms, and also it is highly efficient. The other point is decision trees tend to provide leaf nodes, and these leaf nodes that are the endpoints can help us easily visualize and see what classes are classified in the predictor variables. So that makes it easy when using a decision tree. And this is one of the visualizations from where I was checking for the appropriateness of choosing these models for the algorithm. And we can see that dataset mainly relied on the BMI column that was feature engineered, which proves to be a rather useful column for the model training. And it classified based on various levels. And at each leaf node, we see the distinct levels of the predictor variable. And more importantly, we can see these values here, which are the certainty levels in predicting each of these levels for the predictor variable, and they all have high certainty levels in predicting these. So that and there's a mostly even split of the training data for the model that was used here. So that proves that this utilization of decision tree as a model for classifying this task was appropriate. Before coming to the evaluation metrics, the models were the continuous variables in the models were normalized, and also a log transformation was applied on the age column, since we saw how skewed the age distribution was. Therefore, a log transformation was used, and this log transformed variable from the age distribution was kept in the dataset for later model training and prediction. A principal component analysis on the dataset was also performed, wherein we get to see how large dimension in this case could have a dimensionality reduction, and we get to visualize how these features interact with each other and the relationship it has with each other. The feature principal components with the most variance are picked. The first and the second principal component showed the most variance naturally, and these were plotted against each other. And we see how these vectors pointing in different directions show how the data is varied, mostly centered here. One thing to note very clearly is how the age column and the time spent using technology devices are completely negatively correlated. And this is how the model was built. Proper data encoding with binning of continuous variables was performed for naive Bayes, as it is sensitive to that. And all the categorical columns were also converted to factors, and data encoding was applied for that as well. For support vector machines, we use a copy of the dataset where continuous columns were normalized, since support vector machines tend to be sensitive towards this data. And for both the dataset, we have a split ratio of 70-30 in the training and validation datasets. Decision tree also utilized the same normalized dataset for the prediction. And we saw the appropriateness of the model as I explained before. Coming to the evaluation metrics, I used confusion matrices, precision scores, recall, and F1 scores. Confusion matrices allow us to simply visualize the accuracy of the prediction as shown here for naive Bayes, which is reasonably okay. But the support vector machines and the decision tree models gave very high and impressive scores of 93% and 96%. Decision tree accuracy of 96% did raise concerns that there might be model overfitting issues. But as we see with other evaluation metrics later on, the accuracy of decision tree did not improve, suggesting like an optimal limit, and that is why it was a high score and probably not due to overfitting. Precision scores tell us the exactness of the model, wherein the correct number of positive predictions are given. How many correct number of positive predictions? Recall scores tell us the completeness of the model, where how many correct number of actual predictions are given after model training. And F1 scores give us the harmonic mean of both precision and recall scores. Finally, an ensemble model was built before ensemble model, the model tuning and performance improvements were also done by utilizing various hyperparameter tunings for each of the models. For naive Bayes, we see it did not make much of a difference. And for support vector machines, we do see at what levels of cost parameters and gamma parameters the model performed very well. But the decision tree remained the same for complexity parameter and max depth changes, suggesting there are other factors involved. And yeah, finally, ensemble model was built as a function where it could take inputs of predictions from all three models, and this was checked in individual accuracies and did not prove to be higher than the decision tree, but it was a rather good score of 96%. This ensemble model was applied for new random data to see how well it performs with unseen data and predicts. And we do see there are distinct classes that are identified even with such a short 15 row of new data that was given. And these predictions proved to be correct so far. Thank you.